All right. So today and the next lecture, what we're going to be talking about is addition of angular momenta. But before doing that, I'm going to do a little bit more extended review of lecture 25 because I was using a chalkboard and of course I ran out of time. I'm going to finish it properly and also explain a little bit more or maybe review a little bit more. So if there are any questions, please do ask. There was an important typo in the that's corrected, that del r squared. All right. So the notes as they are on the slides as they are on the website are correct now. Good. If there are any questions at any point, do ask. So we talked about last time, we talked about the Schrodinger equation for central potentials. And we do a separation of variables. This is a three-dimensional problem, but it has spherical symmetry. So we're going to split the wave function into the radial part and the angular part. And then we already solved the angular part. What was the answer to the angular part for spherical symmetry? What are the wave functions? Spherical harmonics, YLMs, right? That's why we're kind of not worried about them anymore. There were the solutions to the radial part of the Laplacian. Yeah, hopefully you recall that, or you could look it up. All right, so here's the radial part of the wave function. And there is definitely labeled by E, that's the energy. And because we're solving the time independent Schrodinger equation, as labeled by L, the angular momentum, right? And the angular momentum, the reason it's labeled by L is that the angular momentum contributes to the Laplacian in this form. Good. So it looks like now it's a differential equation for a function of one variable. So it looks like it's effectively one-dimensional. But to make it really one-dimensional looking, we have to make a change of variables of multiplying this function by r and define function u. Why do we do that? Because if you look at the orthogonality condition for this r, you will have to integrate r star on a solid sphere, on a sphere, on the surface of a sphere, which is dr 4 pi r squared. But using this change of variables, r squared dr. This is properly normalized as you would expect from a one-dimensional problem. So it's just a convenient change of variables. There's nothing profound about it. Now, written as an effectively one-dimensional system, you see that the potential is the contribution from this L term, the angular momentum, is now could be eaten into the potential, and this is some sort of effective potential. This effective potential, what it does is that, you see, it's 1 over r squared. At long distances, it barely changes anything. But at short distances, as the potential becomes increasingly goes towards minus infinity, it lifts it back up and pulls it up. So this is the form of the V effective for L larger than 0, because for L equals 0, this term is simply not there. And we explained the physics of this. Do you guys recall? It's called the angular momentum barrier. What's the physics of this? It's what incorrectly in the pop people usually refer to it as a centrifugal force, right? Something that's spinning that is hard to, it just moves away from the center, right? That's basically the minimum of the potential is moved away. All right. So it's a differential equation. Whether we're solving it on the half line or from 0 to infinity. So as usual, you have to be careful with your boundary conditions. We're going to expand the differential equation near infinity and near near r equals 0. And just use that as an ansatz for the form of the wave function, the radial part of the wave function. Okay. So if you do that, you're going to see that we did that near r equals 0, the center. This is the behavior you expect. And we said that this behavior is ill, not sick. So there was a reason for that. We dropped this term. So B has to be 0 for physical reasons. Do you guys recall why? Yeah, no, but if you pick the wave function with that sign, you will have a problem with it won't be normalizable. So it basically ends up being the whole wave function ends up being well. I suggested I hinted the calculation. It's in the notes. If you calculate the flux associated with wave function in an arbitrarily small circle around or ball around r equals 0, the flux is non-vanishing. That is physically nonsense. But another way of saying this is that you're going to have a hard time making the wave function square integrable. You guys know what square integrable means? A function is square integrable. This integral is finite. If it's finite, you could always normalize it by the value of it. But depending on the function, it might not be the case. Give me an example of a function that's not square integrable. Anything you want, x. anything that grows, right? So anything that has to be, if the function has to, like whatever the function is, has to integrate, the area below this has to be finite from minus infinity to infinity, it better die away at infinity. So any growing function, of course, is not going to be squared, right? Good. These are very intuitive things that, like, it might seem obscured by the fact that you're solving differential equations, but as a physicist, there's a difference between when you solve a differential equation compared to a mathematician solving it. Because you should, every step of the way, you should interpret things, right? And often it's just sanity. It's just requirements are based on sanity. Okay, so b has to be 0, so the behavior of the wave function near the center is r to the power of l plus 1. Near infinity, we saw that the wave function will have to decay exponentially fast, and we call the coefficient that sits here kappa. Kappa is minus 2m e over h bar squared. E is negative because we're talking about bound states. Otherwise, you will have scattering modes. So what's the dimensionality of kappa? Just look at this expression. What should you, as a physicist, what should you think of kappa? 1 over r. It's a length. It's an inverse of a length scale. So 1 over kappa is a length scale that your problem is telling you about, right? And the length scale is controlled by energy and the mass, of course. Maybe. That actually sounds right. Let me. Well, I don't have it here. Let me look it up. Yep, there we go. Thank you. Thanks so much for the correction. That actually kind of makes sense because it's the same thing as when we did the WKB approximation. It's exactly minus 2me over h bar squared. Yeah, thank you. Good. I intentionally put these typos here so that all right. So kappa r is a dimensionless parameter, distance, radial distance now. And we're gonna pick this ansatz to remove, my handwriting might be hard to read. This is L plus 1, and then this is e to minus rho. This is rho. This is rho, right? So now this is the ansatz we're gonna pick, and it's gonna simplify our differential equation based on the behavior at infinity. This is what we found as the final differential equation that is useful for every problem that's spherically symmetric. Any questions so far? There are a couple of examples in Sakurai about this. Actually, in the notes, I included 2 examples, but I didn't have time to go over one of them. One of them is a spherically symmetric simple harmonic oscillator. Do you know in advance what the solutions are? You don't need to. So you go through this differential equation in a hard way and solve all of this, and you discover something that you already knew. You already know it. What are the solutions to different three-dimensional spherically symmetric harmonic oscillator? What's the potential? So the kinetic term, so let's write it down on the board. What is the kinetic term? someone? Minus p squared, and in differential language, it is Laplacian, exactly. So that's going to be del x squared plus del y squared plus del z squared, right, over 2m. This is the kinetic piece. What is the potential piece? Half m omega squared r squared. But what is r squared? R squared is x squared plus y squared plus z squared, right? That's what r squared is. So what is this? This is the Hamiltonian for a simple harmonic oscillator, one-dimensional simple harmonic oscillator in the x direction, plus the Hamiltonian for a simple harmonic oscillator in the y direction, plus Hamiltonian for a simple harmonic oscillator in the z direction. So you know everything you want to know about this. What are the eigenkets? They're labeled by three numbers: nx, ny, and z. What are the energies? H bar over 2 omega, thank you, nx plus ny plus nz plus 3 over 2, because there's a half on each of them, right? Yeah. Thank you. Thank you. So this is the spectrum of it. And what is neat about this is that, well, now you could take this as r squared, and this is, you could write this in polar coordinates, and you could solve the equation, this equation, and at the end, you have something to compare to, and it all matches nicely. Yeah. Is there squared on n terms? No. So what was the spectrum of the simple harmonic oscillator was just integers, right? Yeah. Have a guess what you're thinking of. How often in nature do you get symmetric potential? Give me examples of forces you know. Coulomb potential, that's spherically symmetric. Another one. There are only 4 of them. Right. Gravity, same potential. Now I challenge you to give me another force. What's the potential? All right. So first of all, if there are 2 particles that are interacting, it's very natural that the potential is proportional or only a function of their distance. That's very physical, right? So the distance is going to be a vector, right? Now, to say that it's only a function of their distance and not the angular variable, it means that the potential is like this. These 2 particles, they have a certain amount of energy. As I just rotate them, it's the same energy. So every time you have spherical symmetric configurations, you expect this, right? The opposite would be weird. What is an example of an opposite, another force that depends on, is not spherical symmetric? Imagine you're in some sort of medium that is anisotropic, right? Then the x direction is more dense or wider. Yeah, like it's not rotation invariant. Then you don't expect it, right? So breaking rotation invariance is essential for violating that. But like the spherical cow approximation for physicists is that everything is spherically harmonic, spherically symmetric, like a cow. All right. So here's the potential, Coulomb potential. So I remember when I took quantum mechanics, it took me a long time to understand this very simple fact that in quantum mechanics, they teach you quantization of a hydrogen atom, right? A single electron going around a single proton. Seems like okay, that it was solved. It seems like a very specific problem. But it turns out that solution is pretty much all that you need to understand basics of chemistry, all sorts of atoms. And the reason is simply that you could replace, first of all, so now what is a more complicated atom? It has a bunch of electrons and a heavy nucleus that has a bunch of protons and neutrons. The only force in action inside an atom, for the purpose of this course, is basically electromagnetic, right? So the interaction between each electron, and the center. Now the center of atom is conveniently so small that you could imagine that all the protons are all sitting on top of each other. That's a good approximation. So far, it seems like that's a very good candidate potential. What other thing can mess this up? What other thing, if you have an atom with a bunch of electrons, it's possible that the electrons are going to repel, right? You might worry about that. Turns out that that's very suppressed. So a simple calculation like this will give you the basics of chemistry. It's beautiful that a simple equation has so much power. It's an exactly solvable system as well. That almost never happens. All right, so here's the potential. This D is the, I forget what it's called, and the number of protons, whatever it is called. What else is in the center and nucleus, in the nucleus of an atom? There are neutrons. What's their electric charge? 0, right? It's a beautiful story. Yeah. Maybe look up nucleosynthesis, Big Bang nucleosynthesis. We don't have time to talk about it. All right. So we saw that when we were trying to solve the not hydrogen atom, an electron orbiting the nucleus, there was a scale that appears, this rho naught, right? Oops. And what is it? Oh, sorry, I said scale. It's a number that appears. Rho naught is a number, right? And you can see it in the following way. I wrote it as 2mc squared over minus e. So what's the dimensionality of the thing in the square root? It's dimensionless, right? Z, which is the number of protons, and then alpha, which is e squared over h bar c. It's about 1 over 137. It's called the fine structure constant of QED. So that's just a number. That's a number that this number plays a very, very important role. If this number was a little bit different, we'd have never had atoms. We'd have never, just in the evolution of the universe, it would have never formed. It's just the right amount for the universe to form all sorts of nice chemistry exists because this number is fine-tuned. It is a very interesting philosophical aspect of it to think. If you mess with this number a little bit, atoms won't form, molecules won't form, nothing will really work out as you expect. All right, okay, enough tangents. So here's the differential equation. We saw that this could be solved, and the solutions exist only when rho naught is 2 times n positive integer plus L plus 1. L is the angular momentum. These are the only situations where this solution exists. Do you recall how we derived this? Yeah, so the solution to this is a function that if you don't have this condition, it keeps growing exponentially, it can't be square integrable. The only way for the function to be a wave function is that it has to be square integrable. And then this is the condition. It only exists for these conditions. All right. Now, define little n as capital N plus L plus 1. Then rho naught has to be 2n, right? Hopefully it's clear. Your energies are going to be minus half mc squared, z squared alpha squared over 2n squared. Now you should see why. Do you see from this equation why we define alpha? What's the physics of alpha? Take hydrogen atom, Z is 1, and take the lowest level of hydrogen atom. N is 1. So what's your equation? En is half mc squared alpha squared, right? That is, so the lowest energy electron orbiting a hydrogen has energy half mc squared alpha squared minus, right? So what's the interpretation of alpha? What is MC? What's MC squared? The total energy of the electron. That's all that there is to it. This whole mass, right? And alpha squared over 2 is the fraction of that energy that decides the energy of an electron going around a proton. All right. This is, by the way, Bohr's formula that he just made it up back then. And that was the beginning of quantum mechanics. This number is minus 13.6 electron volt z squared over n squared. This number, 13.6 electron volt, is magical. As I said, it's essential for chemistry and molecules to form. If there was some other number, things will fall apart. All right, we said that several times. Here's kappa. I said that kappa has a length scale associated with it. So what is that length scale? Where take out z over n out of it. It's 1 over a naught, because we said 1 over kappa is the length scale. What is that length scale? It's called Bohr radius. And it's h bar squared over mc alpha. It's Bohr's radius. Every time you see an expression like this, these are constants of nature, right? H bar, mass of an electron, charge of an electron squared. This plays a crucial role in the way that, in explaining the world around us. So it's not an arbitrary parameter you define because it was helping your equations, helping you solve the equation. It's a physical length scale that sets chemistry. Any questions? By the way, do you have a sense of what this distance is? What the length is? What's the diameter of a nucleus of a, what's the size of the nucleus of an atom? Like say hydrogen atom, which is a proton. So what's the diameter of a proton, roughly speaking? Like an angstrom. Well, yeah, 10 to minus 10 meters, right? I don't have it in feet. It's 10 to minus 10, okay? Now, compare that to this radius. Bohr's radius is a scale for the electron going around it. Sorry? Half an angstrom. No, but like it's definitely orbiting outside of the center. So if the diameter of this is an angstrom, this is. Do you have a guess of how much larger it is? Just to have something in mind. We know that it's much larger because we have used the approximation that protons are sitting on top of each other. Right? So here's the center, here's the proton, or a bunch of them sitting on top of each other. Right? So this size, roughly speaking, is an angstrom, and then there's Bohr radius, which is the electron going around it. Of course, it's a cartoon picture, it's quantum mechanics, right? There's a wave function, and the wave function is like spread all over, but this is where it's most likely it's placed. It's much larger. How much larger? Think about this. If you have a calculator, you could do the calculation for yourself. Any guesses? 10. Any other guesses? Something very fundamental about nature, right? How far are electrons from the nucleus? Have you heard of Rutherford? So Rutherford was the guy who took an atom and started shooting things at it. And then he saw very, very rarely, usually things would go through. Very, very rarely, it would hit and just some points in the center and will bounce off. And he deduced that there's got to be a nucleus in an atom. And then he deduced that it has to be, based on how rarely it happened, he deduced that the size of an atom compared to the nucleus, he deduced that this is 10,000 times larger. He was not wrong. Of the order of 10,000. So the nucleus is sitting absolutely in the center. So these protons or neutrons are sitting on top of each other. All right. They there used to be a watermelon model of atoms anyway. Right. People were creative. The eigenvalues. Okay, here's an important comment. What are the energies are labeled by this little n, which is capital F, n plus L plus 1. The point is, the energies do not depend on M or L. Well, the dependence on L is subtle. How do we interpret this? When n is equal to 0, right? L has to be, wait, sorry, my bad. Let's pick a given n, right? So we're looking at all the eigenfunctions of fixed energy, yeah, right? So how many different ways can we arrange for this? First, capital N is 0 and L is n minus 1, right? It's one state with this, well, it's a set of solutions with this energy. How many such states are there? How many states with this L are there? One? Any other guesses? N? No, well, like I fixed capital N, so here's what I'm doing. Fixed. En, I'm looking at the number of contribution, the number of states that have this energy. So one way to arrange for it is this setup, n minus 1, right? Yeah. Okay. So how many states with this configuration are there? 1. Sorry? 12 plus 1, exactly. This has angular momentum L. Remember that we were talking about these in terms of YLM of theta 5, and M runs from minus L to L. So there are 12 plus 1 states of this, right? Then another way for the same guy, you could arrange for it by having this configuration. How many configurations, how many states of this form are there? Sorry, 2. Yeah, so 2n minus 1 plus 1. This is 12 plus 1, right? So this is n minus 2 plus 1, and so on. What is the largest that it could be? N can be n minus 1. This is L equals 0. For every given n, there is a state with no angular momentum, right? And as you increase the angular momentum, you could also still arrange for the same energy. All right, so these are all states of the same energy. How many of them are there? Let's sum them up. There's n squared of them. So there's a lot of degeneracies. Is this clear? Any questions? Yeah. What's that? Oh, the solutions are labeled by this. You're asking what's the physical meaning of it. There's no clear physical. If you wish, it's energy minus L minus Y, right? Capital N itself is just something that came out of the counting solutions of the differential equation, but it's nicely related. That equation relates it to angular momentum and energy. It doesn't have an independent interpretation. All right. When all the dust settles, here are the solutions. An electron rolling around a nucleus. So the wave function is now, this is the wave function for energies are labeled by little n, and of course LMs, right? So here's the radial part. Here are the YLMs, and the radial part is this equation. We just plug in everything in there. This is an explicit solution. What's the name of this? This is a confluent hypergeometric function. How many of you guys have heard of hypergeometric functions? Okay, let me just tell you one thing. I don't know if it's helpful or not. at first, it might look like a lot of these functions they appear all over the place in physics. It looks like bookkeeping. People have these tables of functions, but there is a lot of structure to these guys, an incredible amount of structure. But let me give you some basic idea of how it's going to be like. There are polynomials and exponentials and those functions that you're familiar with. I'm not going to tell you its story. There's something called Fuchsian differential equations, but one level of complexity beyond that are Bessel functions, right? So Bessel functions are one level of complexity beyond that. One level of complexity beyond that, hypergeometric. One level of complexity beyond that, you probably never work with it, is point functions. Anyway, so there's a structure, a lot of structure to this. And yeah, good. So these are hypergeometrics. This is actually the confluent hypergeometrics are very, very special ones. So, yeah. Any questions? So this was a summary of the last lecture, an extended summary. Yeah. Absolutely. There's a theory of Fuchsian differential equations. The way you look at the functions is the number of poles in the equations. If it has one pole, it's a very, very simple structure. If it has two poles, it will be Bessel. If it has three poles, it's hypergeometric. If it has four poles, it's point. And then there's a zoo of poles as it gets larger. There's some physics associated why there are these poles, what's the physics of them, and all of that. If you ever do scattering theory or whatever you're doing, you're going to learn all about this way more than I understand. Yeah.
I think earlier when you said the size of the nucleus and the size of the atom,
yeah,
the nucleus is more like 10 to the negative 15, and the whole atom is negative.
That's right. Actually, yeah, you're absolutely right. So the nucleus is 10, it's a Fermi. Sorry about that. Yes, the atom is 10 to minus 10. Thanks so much for the correction. So it's 10 to minus, yeah, 10 to minus 15. That's more like 10 to 14, minus 14. It's like a couple of Fermis, 10 to minus. Thanks so much. That's an important correction. Yeah. 10 to minus 10 is the size of the whole thing. Yeah. All right. You can tell I'm not the theorist. It's a relative scale that matters. All right. So today's lecture. Are there any questions? Because we're going to change gears. Let me just say something fun. So the size of a proton is 10 to minus 15. It's Fermi, right? It's insanely small. You've heard of gravity waves. So gravity waves were first detected using an experiment LIGO in Arizona. There are two rods, metal rods, perpendicular, and they're 4 kilometers long or 4 miles long, 4 kilometers, I think. And then you have to measure when the gravity wave goes through this, you have to measure the length of this rod really, really well. And based on that, you deduce that space-time stretched as the wave went through. The error bar, the amount that the length of the 4 kilometer rod changes as the gravity wave goes through is about the size of a proton. And we can detect that. People can't detect that. It's mind-blowing. Anyway. All right, so addition of angular momentum. Are there any questions? Because this is really a change of topic. All right. So previously we talked about two different things. One was spin, and the other one was, we called it orbital angular momentum. Right? We said that spin had to do with some sort of an intrinsic property of the particle, right? And orbital angular momentum had to do with just r cross p, right? So we also said that the orbital angular momentum, the function, the operator we talked about when we quantize it, acts on the spatial part of the wave function, whereas the spin operators act on that spin part of the wave function, right? It's just some sort of a. And then, if you recall, there's a tensor product structure between them. These are independent degrees of freedom, right? So the Hilbert space has the spatial part, tensor, spin part. These are completely independent degrees of freedom. Sometimes people talk about, when you talk about orbital angular momentum, well, people talk about orbital angular momentum versus spin angular momentum. That terminology people use. I don't like it, but good. All right. So what are the wave functions here? An arbitrary wave function, let me call it psi, is going to be, by the way, sorry, this notation, I'll use it a million times. A lot of times when I have something like alpha tensor beta, or let me actually write something that's more closer to what I use, M1 tensor M2, I often write it as M1, M2. Otherwise, all the equations will have a million, gazillion tensor products. Okay. All right, so here's a wave function. And the interpretation of it, well, there is two components. It has two components, right? Each of these guys have to do with spatial part, and then two components have to do with spin. Psi plus minus x prime squared is the probability of finding a particle of spin half in plus half or minus half state at point x prime, right? This is just notation and foundation of what these wave functions are like. Good. All right. Now, when we were talking about spin, we did not care about the spatial part of the wave function. Then we started talking about orbital angular momentum. I said, forget about spin. We're going to think for a little bit about particles that don't have spin. But what happens if you have a particle with spin and you're applying your rotation to it, keeping track of how the rotation acts on the spatial part of the wave function? This is the question. So the total angular momentum, J, is the orbital angular momentum plus the spin angular momentum. But what this equation means, this is, you have to get used to this combined notation that physicists use. This means that the orbital angular momentum operators L tensor identity acts in HS, wow, plus identity tensor S, this acts on HX, HS, HX, right? So when you do apply rotation, the spatial part of the wave function is going to be acted on by the representation of the rotations that we discussed using L's. Tensor, the spin part of the wave function is going to rotate by the representation of rotations in the spin Hilbert space, right? Good. So for a spin half particle, what are these matrices? What's the size of them? There are 2x2. There are 2x2 complex matrices, unitary matrices. There are SU2 matrices, right? So here's how the rotation is described for a particle with spin. For the purpose of this, most of what I say, we keep in mind like an example where a spin is half, so that it's easier to keep track of things, but it's fully general. Good. All right. Let me pause here. Is this clear? Something interesting happens. So remember the orbital angular momentum, we described that there were two operators that were simultaneously commuting, L squared and LZ. We described it using the eigenkets of these guys, simultaneous eigenkets of these guys, ket LMs, these were related to YLMs. YLMs are just spatial part of these. And they satisfy these eigenrelations, right? L is from 0 to infinity and M is from minus L to L. For the spin part, the eigenkets were the eigenkets of S squared and SZ. We use the notation of JM for it. J is 0, half, 1, blah, blah, blah. And M is from minus this, that. The only difference, the representations are very similar, except that for spin, you're allowed to have half integers, right? Whereas here, you can't have half integers. That half integer had to do with the fact that as you go around by 2 pi, you could pick up a minus sign. Good. What happens in the next slide, actually, well, not next slide, the next couple of slides will actually be a concept that will be important, very important in physics. we're gonna do a lot of calculations, and you will have to do most of it. I just show you some of the results. I'll do sample calculations, but the calculations are necessary for the principle to click, and I absolutely recommend doing this. Okay. What is the idea? The idea is this. You have an operator S1. So what we would like to do is we would like to talk about how rotations act on a particle with spin, how it acts on the whole wave function, the spatial part and the spin part, right? So we would like to talk about these transformations. Now, let's do what you see in this structure is that your angular momentum is the sum of two terms that are commuting, right? L tensor identity plus identity tensor S. Let's do a warm-up calculation. Let me clarify what I mean by warm-up calculation. Here, L, if you had, so what are the eigenkets of L? These are LMs. What is the dimensionality of the Hilbert space? It's 2L plus 1, right? So this is your HL that you're tensoring, say, if you have spin half. This is two-dimensional. This is two-dimensional, and then this is 2L plus 1 dimensional. Before getting into that complicated example, let's start with a simple example where this is also two-dimensional. So a physical example of that would be a setup where you have two spin half particles. So here's spin half particle 1, spin half particle 2. There is S vector of this guy, S vector of this guy. If you recall, we had this composite system axiom or assumption in quantum mechanics that the Hilbert space is the tensor product of them. So the total spin for two spin half particles is going to be the spin of the first particle plus the spin of the second particle, and this is the structure of it. Good. In terms of commutation relations, these guys commute, of course, but each of them individually satisfy this SU2 Lie algebra. Any questions? So this is what we're gonna be talking about. Now, I believe the next slide is where everything becomes important. Is the setup clear? I just have two qubits, right? The total spin is the spin of the first one plus spin of the second one. The issue is this. Let me just say it in words. So you know how to describe the Hilbert space of this guy? You know how to describe the Hilbert space of this guy? What is the total Hilbert space? What's the dimensionality of it? Sorry? Yeah, but there's two qubits, 4 dimensions, right? But this operator, so this operator could be viewed as, it's a total spin. So this guy will also have eigenkets. And the eigenkets of this guy and these guys might not match. We'll see that in a second. All right. So there are two bases to describe this 4-dimensional Hilbert space. Two qubits, right? Let me remind you what the notation. This was 1, 0. Sometimes I got this is 0, 1. Let me write it this way. 1, 0. I think we use this notation S of Z. Oops. S of Z plus. Sometimes we wrote this as plus and minus. No. S of Z minus. This is minus plus H bar over 2. Hopefully you recall. Minus H bar over 2. 0 and 1. Minus. Right? This is a notation we're going to be following. So when this is each of the Hilbert space 2-dimensional. When you tensor them, what basis can you think of? Well, there is this state, which is this. There is this state, which is this, and 2 other ones, right? You guys. Hopefully you recall how to write them as vectors, 4-dimensional vectors. What's the top one? 1, 0, 0, 0. Okay, good. Good. So this is one basis. And this basis has the property that these vectors, these 4 vectors that we're talking about, they're eigenkets of S1Z, S2Z, and well, S2, S1 squared, S2 squared, right? So these vectors are the eigenkets of S1Z, which is this operator. I don't know if you see from there. Let me write it over here. So these four vectors, which are where the simultaneous eigenkets of S1Z, which is SC tensor identity, S2Z, which is identity tensor SC, and S1 squared, let me write it this way, and S2 squared. Right? Is that clear? In general, because I don't want to keep track of this, sometimes I write them as M1, M2. But M1 and M2 take plus minus values. And you can see how the generalization will work. Right? If I have a spin S particle, now these M1s and M2s run from minus S to S, and they take two S plus 1 values. Yeah.
What about S1Z tensor S2Z?
S1Z tensor S2Z. Well, if it's an eigenket of this, it's an eigenket of that, is it an eigenket of both of them? Them multiply. Yeah, because they commute. Because they commute, that's important. All right. But there's another basis. This point, this slide is very important. It's like basically what decides the rest of this section of the course. The second basis is in terms of the total spin. The total spin, the Z component of it is S1Z plus S2Z. And the total spin squared is S1 plus S2 squared. You could talk about the eigenkets of these guys as well. These bases, these bases do not match because S2 does not commute with these operators. I'm going to pause for a little bit for this to sink what is going on. The total spin in quantum mechanics, this is one interesting phenomenon. The total spin, if you know the spin of this particle, you know the spin of that, if you take an eigenket of this spin, an eigenket of that spin, put them together, that's not the eigenket of the total spin. That's the message. And how to relate them is through coefficients called Clebsch-Gordon coefficients. You have to rotate your bases using unitaries. We're going to calculate them, and that's going to be the next couple of lectures. Right? When you put spinners together, the total spin is not simultaneously diagonalizable as individual spins. Okay? All right, so let's talk about the second basis. So what are the eigenkets of total spin? The total spin is squared, is S1 plus S2 squared. That's S1 plus S2 dot S1 plus S2. That is S1 squared plus S2 squared plus 2S1 dot S2. Are these equations clear? The notation is clear. So when I write S1, 2, that's what I mean. Right? Similarly for S2. Yeah. This one?
Yeah, that one. S1 plus S2 minus plus S1 plus.
Oh, that's the typo. Thank you. So let me get there. Yeah. So this is the first equation. Then what you would like to do is that you would like to expand this term. This term is what's giving you hell. If you expand this, what is this? This is x s1x s2x plus s1y s2y plus s1z s2z. But the sx and sy part of it, you can write it nicely in this form. So this is a rewriting of the total spin operator. Good. What are we trying to accomplish here? I'm gonna act on one of these vectors, doesn't matter what. Pick this one. And show that this is not an eigenket of the total S squared. It's not. So we'll need a new basis. Is that what everyone is good? What we're gonna accomplish? All right. So the notation might be a little bit confusing, but unfortunately, well, it's good to get used to it in this simple setup as we go to more complex examples. The notation is very helpful. So these kets take up, up, and down, down. They're actually eigenkets of the total z components of the spin as well. So why is that? Let's act with SZ. The ones that don't have the label 1 and 2 are the total. Okay, so this is S1Z plus S2Z. This is H bar half plus half, H bar. S1Z plus S2Z minus half minus half minus H bar. Good. So far, easy. Now, let's act with S1 squared plus S2 squared. Well, these kets are, of course, eigenkets of those guys as well. What are the eigenvalues? What's the eigenvalue of, for example, S squared acting on this guy? S1 squared acting on this. It only acts on plus, right? So it's going to be H bar squared half times 3 halves plus 1. Right? So because I have two such terms and both of them are spinners, you get 3H bar squared over 2. Good. So far, no trouble at all. Now, the piece that's left is this term. Here's where things get a little bit funky. Well, actually, no, not for these two states. These two states are okay still. First thing, notice that, well, what is the action of S1Z, S2Z on this ket? What's the result? S1Z, S2Z acting on plus plus. It's H bar squared over 4, right? Because each of the SZs will give you H bar over 2, right? Okay. But these operators are going to be a little bit tricky. How does this guy act on plus plus? What does it do to plus plus? It kills it because S2 plus acting on plus is 0. We can't raise it further. How does this guy act on plus plus? It kills it because S1 now kills it. So all that you're left with is H bar squared over plus plus. Similarly for minus minus. Good. Putting everything together, you learn that the ket plus plus and minus minus are actually eigenkets of the total S squared with eigenvalue 2H bar squared. We're going to call these guys ket S equal 1 M plus minus 1. Why? Because they satisfy these relations. I think this needs an explanation. Let me do that. So what did we find? We found the following. We found that if you take, let me write this here. So this is S1 plus S2 squared, and then SZ is S1Z plus S2Z. We took plus acted with S squared or minus minus, and the result was 2H bar squared plus minus minus. We acted with SZ on plus minus minus. The result was plus minus H bar plus minus minus. Okay. So it's a simultaneous, these guys are simultaneous eigenkets of these two operators. Pay attention to the eigenvalues. What is the total spin that this guy is describing? Remember the eigenkets of S squared? We wrote them as Jm, and the eigenvalue was H bar squared, J plus 1, Jm. So this equation compared to this tells you that what is J? 1. All right. So these kets correspond to J equal 1. How about M? So look at this guy. He said S of Z acting on Jm was MH bar Jm. So comparing these two equations, what is M? Plus plus has plus 1 minus. Right? So this notation is justified. So up, and downs are okay. You should be, there's already something funny going on. Right? What did we find? We put together two spin half particles. We saw that two of the eigenkets we already had correspond to a spin 1 particle. How many eigenkets does a spin 1 particle have? 3. So we're missing 1. We're going to find that one. But we had 4-dimensional Hilbert space to start with. So there has to be yet another vector. Right? All right. Good. So what is the eigenket that is spin 1, but m equals 0? Here's that eigenket. We gave this kind of states a name. What did we call them? Entangled states. These were Bell states. Yeah, we also gave them other names. We'll give them other names, right? Okay, so let's act with SC on this vector. If you act with SC on this vector, you're going to get H bar. Actually, wait a second. Is this correct? Yeah, that's correct, actually. You get H bar minus H bar and it's 0. This justifies, comparing this with that equation, this justifies that this is m equals 0. If you act with S squared on it, let's see what do we get. All right, is this part okay? Is this part everybody's good with me? This calculation is a little bit more involved. Let me write down what S squared was. So we wrote it in a suggestive way. We wrote, well, is this also equal to S1 squared plus S2 squared plus 2S1Z S2Z plus S1 plus S1 S2 minus plus S1 minus S2 plus. So first I'm going to take this piece because it's easy. All right? Let's act on these two kets because these are the kets that we have. S12 and S22 will give you these terms. Is that clear why? Because each of them are these are eigenkets with eigenvalues H bar squared over 3 times 3 over 4. Now this term will give you 2. SZ will give you, acting on the top one, give you plus half, bottom one minus half. S2Z acting on this guy gives you minus half, bottom one plus half. Good? So you add them up. This is 3 over 2 minus half. You get H bar squared. So these vectors are also eigenkets of this piece. Now, this is the term which is going to mess up everything. How does S1 minus S2 plus act on plus minus? This guy will bring plus down. Oops. This guy will bring plus down to minus. This guy will raise minus to plus. And of course, the other term will vanish. Similarly here. So what do we find? We find that if we act with, let's do this exercise with me, S1 plus S2 minus plus S1 minus S2 plus acting on plus minus, right? So what does the first term give me? Up to coefficients. I'm going to get the coefficient from. No, actually, the first term will give you 0. The first term will give you 0. The second term will give you h bar squared minus plus. So clearly, this vector is not an eigenvector of S squared. Is that established? Because the vector changed. But if you do the calculation for this guy, you're going to get this, which means that if you add the two vectors, now you're going to get an eigenket. You just put all of this together, you realize that S squared acting on this gives you 2h bar squared, this vector. From this, you conclude that this entangled state is actually the missing vector eigenket with m equals 0, spin, total spin equal 1. This is a particular entangled state. Good? I'm really behind. No, I'm good. All right. So we found 3 vectors. These are describing a spin 1 particle. The up and down were things that we knew. We saw that the m equals 0 component of the spin 1 particle ends up being an entangled state. The Hilbert space is 4-dimensional. This is the only orthogonal vector that remains. This is called a singlet state. It's another entangled state. If you act with S squared and SZ, you're going to find that it corresponds to spin 0, m equals 0. What did we find? Let me write it here. We took a 2-dimensional Hilbert space, this notation, right? This is, I'm writing this, this is not to be taken literally, although there is such a notation in math. We took a 2-dimensional Hilbert space. We tensored it with another 2-dimensional Hilbert space, you get a 4-dimensional Hilbert space, right? The basis that describes these were these guys. We wrote this as a 3-dimensional Hilbert space that corresponds, so this is spin half, this is spin half. That corresponds to a spin 1 particle. These are plus plus, minus minus, plus plus, plus minus minus, 1 over square root cubed. There is an orthogonal state, direct sum. I've not explained this. 1. This is a spin 0 particle, and its vector is, this is called the singlet state. So when you put together 2 spin half particles, the total spin could be 0 or 1. You might have been tempted to say that, oh, sorry, this is wrong. You might have been tempted to say, oh, this term alone has spin 0. That's incorrect. Quantum mechanics picks the entangled state with a plus sign as the one that has spin 1, has spin 0. All right? Okay, but you will have to do this for yourself for it to slowly. And I can redo some of the calculations. I can do some of the calculations here, but at the end of the day, you will have to reproduce them because you're going to see it gets more and more complicated. So what did we find? Here's a 4-dimensional Hilbert space. Here's the other 4-dimensional Hilbert space on this side. We found that S0, M0 is this vector. S1, M1 is this vector. S1M0 is this vector, and S1M minus 1 is this guy. This is a unitary rotation of the four-dimensional Hilbert space. Can you guess what it looks like, that unitary? What does it do to plus plus? Plus plus is 1, 0, 0. It's 1 here, it's 1 here. What does it do to here? All right, I will not fill up this table, but these are the exercises you should do. You should write down the four-dimensional vector space here, four-dimensional vector space as a unitary that rotates the bases, and I'm giving you all the equations, right? The matrix elements of those unitaries are called Clebsch-Gordon coefficients. It's these coefficients: 1, square root 2, 1, minus 1 over minus 1 over square root 2. These are called the Clebsch-Gordon coefficients. And they come up every time you put together two spin degrees of freedom. The total spin, the basis that diagonalizes the total spin, is not the tensor product of the basis that diagonalizes individual spins. You need to rotate the space unitarily, and those their unitary rotations are matrices. The matrix elements by matrix, every matrix element is called Clebsch-Gordon coefficient. I can assure you it will come up in your life, maybe in your final exam, but it will come up. All right. I'm gonna summarize. Right. I'm gonna focus. Forget about the central forces, all of that. I'm gonna focus only on the ending. Right. What happened? We took two spin degrees of freedom. If we had measurement devices that could isolate them, measure this guy separately, using this basis was very natural. But if you had a measurement device that only could not distinguish the two, could only sense the overall spin, how the whole thing responds to, say, magnetic field, you would find it to be, the thing is, the system, you would describe it as spin 1 particle, degree of freedom, next to a spin 0. Now, this is called direct sum. What direct sum is the following. Let me describe direct sum. So you know direct product. When you direct sum two matrices, if this is a D by, if you direct sum two Hilbert spaces, H1 plus H2, the resulting Hilbert, so if that's you mention D1, this is dimension D2. It's the most naive thing you would think. Just take a vector that has length D plus 1 plus 2, to copy this vector here and this vector here. You just put them next to each other. Now, if you have operators, if you have two operators, A1 plus A plus B, and this is, I don't know, D by D, and this is D1 by D1, this is D2 by D2, you describe the direct sum as a D1 plus D2 times D1 plus D2 matrix, where A is this block, B is this block, and the rest is 0. This is called direct sum. To contrast it with direct product, sorry, tensor product. Tensor product is when the dimension of the Hilbert spaces multiply. Direct sum is when they add. There is plenty of physics that distinguishes them. What was the physics words that we put to to tensor product? We said tensor product describes degrees of freedom that are independent. You have two particles, you describe the Hilbert spaces as tensor product because the number of options multiply. Direct sum is something else. It's another operation you haven't seen yet. Well, you sort of seen it, I have not explained it. We'll describe this in the next couple of lectures, all right? So, Clebsch-Gordon coefficients come up when you take the you rotate from the basis that diagonalizes the local spin degrees of freedom to the global degrees of freedom. Are there any questions? Yeah.
So tensor products describe composite systems. Direct sums also describe. They don't describe.
No. So direct sums, I have not described to you what they describe, but it's an operation. Let's just, I'll tell you what it is, but the operation is well defined. Let's just first make sure you understand what the operation is. When you direct sum, you're adding the number of options, right? When you have composite systems, the number of options multiply. If you have a string with 2 options and a string with 2 options, the total options are 4. You multiply. Well, 2 and 2 is a bad example because of addition, right? But in direct sum, you're adding them. Think about actually what the physics could be. There's something profound here, but we have not described it. All right, any last questions? But if you want a word, charges. Charges are described by direct sum. We'll get there. Thank you so much, guys.